So we choose a key from this key space, little k, and we provide A with that oracle. Or we choose a random permutation and provide A oracle access to that. So to say this is asymptotically secure, what we're saying is E is PRP secure if for every adversary, but what kind of every adversary? Anybody remember? What resources do we give to this adversary? So what does reasonable mean more concretely?
It means they don't have infinite resources.
It means that it's probabilistic. It could make its own coin flips.
Yes.
And it runs in polynomial time.
Yeah.
So for all probabilistic polynomial time adversaries A, the function of the advantage of A is a negligible function of K.
Where do you include the security parameters?
In here.
No,
It's right here. Why not? I mean, I'm not saying it's a key generation algorithm. I'm saying it's drawn from a key space. Why doesn't that work?
Normally, I mean, the EK should also the domain, I mean, the none of the input should also change.
Change like the asymptotics.
Right.
Okay. All right. Well, let's move on because James disagrees with me. I'll get back to asymptotics a little bit later because I have something he's not going to disagree with. Okay. So let's move on to the notions of encryption. So again, we're going to give the adversary a distinguishing game. In the real world, we choose a uniform random key, and she's given access to an encryption oracle. So this is for probabilistic encryption. So here she asks messages, and she gets back ciphertext. Okay, so I'm now describing the indie $sign notion.
Wait, really quickly, you were talking about the PRF
Oh, yeah.
for switching lemma.
Yeah.
Are you going to continue on that?
Well, okay, so all I was going to say about that is, yeah, sorry, we got a little sidetracked there. The q squared divided by 2n plus 1, 2 to the n plus 1, what that means concretely is what is the probability of seeing a collision. So you're interacting with either a random permutation or a random function, and if you ever have two distinct queries that map to the same value, you know you have the random function and not the random permutation. Is everyone clear on that?
Let's repeat that.
Yeah. I'm sorry, guys. We got a little sidetracked. So, normally we call random permutations pi, and we call random functions rho. So the difference between these two, pi is a bijection, meaning it's 1-to-1 and onto. That this is not. It's not necessarily 1-to-1. So that's the difference between them. So if I ask a bunch of queries to my oracle, and I get back a bunch of responses, y1 to yq, if these are all distinct, and I notice that one of these is non-distinct, I know I must not have the random permutation. I must have the random function. Yeah.
And the bound doesn't strictly get rid of that, right? It just makes it improbable.
What the bound says is that if A is interacting with one of these two worlds, what is the probability? Okay, when she's given this oracle, what is the probability that she sees a collision? And that's what the birthday bound is.
Can you repeat about the part about distinct? You were saying that if all are distinct, one of them is, I missed what you said.
So if all of her inputs are distinct, all of her queries to her oracle, which is either a random permutation or a random function, if all of them are distinct, and then all of the responses she gets back are also distinct, that means, well, she can't tell whether she has a random permutation or a random function. Because as far as she knows, everything is one-to-one. Now, if she sees a collision, so one of these y sub i's is equal to one of these y sub j's, then you have a collision, and that can only happen if you have the random function oracle.
I have a question, like, on the midterm overall. Is it going to be more, focused on, like, little specific details, or going to be more focused on, like, a sort of a higher level understanding? Because I want to know if, like, do I have to go back and review each type of encryption we've used so far, like SHA-220, AES, RC4, all that stuff?
The details of so the details of like block ciphers or stream ciphers, those constructions, I wouldn't worry about too much. You need to know, for example, what a Feistel network does in general.
Okay.
And you also need to know what are the modes of operation for encryption. So we're mostly interested in your understanding of higher level goals. So CVC mode, counter mode. What do these mean? How can you use them? You could use a random IV, you could use a counter IV, you can use a chaining IV, or you can use a stateful IV. That sort of changes depending on how long the messages you've encrypted are so far. And what time? When is it secure to use one mode of operation and not another? You had a question?
Going back to this.
Yeah.
The birthday bound, it doesn't say that, it doesn't guarantee a collision, right? It just says that it's probably going to have a collision.
It gives you the probability. Once you've asked Q queries, what is the probability of a collision?
So.
Yeah. Actually, go ahead.
So it was kind of, what was he saying? It was like the key exhaustive search. He said that if you run a key exhaustive search, that you're not gonna, like, the worst case scenario is the whole thing, but you're gonna find it somewhere in the middle, probably. And I don't know. I thought it was kind of like that. Like with the birthday bounds.
The birthday. So doing exhaust. Are you talking about man in the middle attacks?
You know what? I'm wording it weird.
Yeah, that's different. Something different. Yeah.
So I guess specifically my question is, given the birthday bound, is a collision impossible?
A collision is, you're never going to see a collision if you have a random permutation. The probability of seeing a collision when you have a random permutation grows as you make more and more queries. So that's the takeaway.
Any function or permutation?
The second one you meant function.
Yeah.
Yeah.
Thanks. Other questions about the PRP, PRF switching lemma?
Is there a difference between the $sign and a pi?
Yeah. The $sign oracle. So for example, if you're talking about PRGs, the $sign oracle just means give me a random string each time. If you, okay, that's a bad example. Actually, let's talk about probabilistic encryption. So if you, the $sign oracle, if you ask it the same message twice, you're gonna get, with high probability, you're gonna get two different strings back. But with a permutation, if you ask the same query, you're gonna get the same value back both times. That's the nature of a permutation. So this $sign oracle is representing something that's not functional. It's just give me a random string. So for example, okay, never mind.
Wait, could you break that? Yeah, because you just asked the same thing twice, and then one would.
So if I ask this encryption, in the Indy $sign experiment, if I ask the same message two times in a row,
the same thing.
I should get something different back. For probabilistic encryption, that is important.
Yeah.
Yeah.
for the real oracle.
So,
But for the real oracle as well.
yeah, for real oracle as well.
That's
yeah.
why it's probabilistic.
So, but for a permutation, it better be a permutation. Because if you ask x twice of your oracle, and you're not getting the same value back, then you don't have a permutation. In fact, you don't have a function. You just have something that's just yelling at you, like in this world. Yeah.
What if you compare the $sign oracle to the random function?
Why?
Are those like similar?
They're not similar.
They're not similar. Yeah, you're gonna see collisions immediately with your $sign oracle. So in particular,
You mean with your random function?
no, with the $sign oracle. So you ask $, give me x, and then you ask that again, you're gonna get two different strings. If you have a random function or a random permutation, you ask x twice, you're gonna get
The same thing.
the same value back twice.
Yes.
So for the permutation oracle, you said the bound is q squared over 2n plus 1?
Yeah, this is the distinguishing advantage A has
Okay.
when it's trying to decide, do I have a random permutation or a random function.
Okay.
So, in particular, the advantage of A, James, let me know if I don't have this right, is the probability that A is given a pi oracle and outputs 1 minus the probability that A is given a random oracle, outputs 1. What the PRP PRF switching lemma tells you is that this is at most q squared over 2 to the n.
Plus 1.
Plus 1. Thanks. Did I answer your question, whoever that was?
Yeah.
Other things?
Can we just move on to something that's not this?
So does the
Yeah.
So does the mix up operations for the Berkeley bound help it to distinguish if whenever we're trying to solve it, it's permutation or function?
So the proof that Professor Rogaway sort of hand-waved a little bit was what happens if I take CVC mode and I use a block cipher with a random key. What if instead of using the block cipher with a random key, I use a random permutation? Now, what happens if I use a random function instead of it? So now it's not really going to be, you can't do CVC mode with a random function, but you can still talk about it. And so what is my distinguishing advantage between those two objects? So that's how it's useful. The PRP PRF switching lemma gives you a bound on the maximum advantage that the adversary gains when distinguishing between those two types of objects. So let's move on. It's a good idea. So we want to spend most of this time talking about any questions you have beyond, yeah. So y'all are familiar with Indy $sign security, right? But I'll just write it out one more time explicitly here. So this is the encryption scheme. It's a triple of algorithms KEP. The advantage of A in the Indy $sign sense is the probability that we choose a random key K. We'll leave that implicit. And she outputs 1 minus the probability that we give her a random oracle and she outputs 1. Who can tell me how LR security works? Anybody? Yeah.
You give it like two messages concatenated together. Like one's the left message, one's the right message, and you have to distinguish if it's the left message getting encrypted or the right message getting encrypted.
Yeah. So in both experiments, in both worlds, we choose a random key, and then we give her an oracle. So this function right, it takes in two plain texts, and it outputs the right one, right? And then we encrypt that value. In this world, it does the opposite. It takes the left one. And she's asked two queries, and she gets back a single ciphertext in response. And she's trying to decide, is C the encryption of M0 or the encryption of M1? And as usual, her advantage is the probability. Where did I write that? I didn't write it. Wait, yeah, I did. It's right there. The probability that she's given this oracle and outputs 1 minus the intent is that she outputs 1 if she's given the right oracle, and 0 if she's given the left oracle. Okay.
Quick question.
Yeah.
I thought right and left are supposed to be switched in that.
It doesn't really matter.
Okay.
The definition is still the same. I like doing it this way because this means if I mean to say I have the right oracle, I mean I'm getting encryptions of M1 as opposed to M0. So I should output M1 if I'm getting encryptions of M1, and I should output 0 if I'm getting encryptions of M0. So that's why I like doing it that way.
The point is that for the same adversary, if he simply flips the output bit, then this advantage would be just plus or minus.
Exactly.
So it really doesn't matter the order. The order really doesn't matter. The definition would all be equivalent.
Okay, so I'm not going to go through the proof, but I want to remind you of what it means. Like if we have two definitions, why do we have two different definitions of encryption? The answer is that we can prove that $IND security of a particular encryption scheme implies left or right security of that same encryption scheme. So, so this is where I wanted to remind you of. This is where So, what does this mean? Well, so you could state the thing asymptotically, and you would say, for all probabilistic polynomial time adversaries A, if the advantage of A in the Indy $experiment, and again we're going to parameterize this by a security parameter K. And what is this K going to do? It's going to be the input to our key generation algorithm. So if you have it here, so if I want to add this to this, make this the sort of setup to this experiment, we would choose a key from the key generating algorithm, which is now going to be parameterized by this little k. Everyone with me? So to talk about things asymptotically, we have to change the syntax a little bit. So this, we're going to talk about the advantage of as being a function of the security parameter k. So to talk about this concretely, asymptotically, we have to basically we're going to say k is an input to the key generation algorithm. Remember that pi, an encryption scheme is a triple of algorithms k, e, d, where k and e are probabilistic and d is deterministic. So k is now going to have an input, which we call the security parameter. Clear?
Yep.
So if this is a negligible function for all probabilistic polynomial time adversaries A, then that implies that for all probabilistic polynomial time adversaries B, the advantage of B against the same encryption scheme in the LR sense is negligible. So to prove this claim, we would prove the contrapositive. Namely, let's assume there exists a probabilistic polynomial time adversary B such that this function is non-negligible. Then we would prove via a reduction that there exists an adversary A such that this function is negligible.
Are you going to do that?
I can if we have time, but I wrote it out, but I wasn't planning on it. Anybody have questions about that?
So I asked this in class, but I still don't really understand it. So, if there exists an adversary that can break the weaker security, weaker in quotes, then there exists another adversary that can break the stronger one.
No, it's
In
Yeah.
fact, yes.
yeah.
Yeah, it's weirdly
Why?
counterintuitive.
Why?
Because we can prove it.
Well, because it's weaker in the opposite sense. It's not weaker in the fact that it's like a weaker definition. So
By strong and weak, we mean that a strong notion, a scheme satisfies the strong notion, always implies that this scheme also satisfies the weak notion.
So the weak notion is actually stronger?
No. And it's all about the logic of this definition. Definition of security says for all adversaries, he can't win. So if you are talking about the existence of adversary, then things become universal.
Yeah.
Yeah,
because a strong notion implies better security, right?
Right.
Yeah.
I think there's like a strong notion that's like more specific. Like it's like
It means the adversary has more power, yet it can't win. And that's a stronger notion.
Yeah.
So
it's a little bit, twinked, or I should say twinkled, but we're not talking about strong and weak, just don't focus too much on these two words.
Yeah.
They can mean different things.
Something to be strong, it also has to satisfy the weak one.
If something, what this theorem tells you is that if something is ND $ secure, it's also LR secure. The converse is not necessarily true. In particular, LR security does not imply ND $ security. That is the sense in which it is stronger. It implies the weaker definition. So if you have something, if you have an implication and the converse does not hold, then the thing on the left side is properly stronger. Yeah.
So have you seen the midterm yet?
I am pleading the fifth.
Okay.
You've seen it.
How likely do you think it is that there's going to be a reduction on there?
You need to know what a reduction is. Reductions are typically hard. They take a lot of time. I would say the best way to practice would be like prove to yourself this theorem. Prove to yourself, for example, that LR security and
implies
ND1
or
or
ND2.
ND2, but they're actually in that case equivalent. So I would not put too much stock into it. The most important thing is definitions.
Okay.
Yeah.
Okay, sorry, I'm just gonna try to rephrase my question one more time. So let's say the ND $ it has a set of locks, for example. The more locks you have, the more secure it is. Let's just say it is.
So it's like this has one lock and this has two locks.
Exactly.
Okay.
Right. So if I'm trying to break into some place and I can unlock one of the locks, why does it mean I can also exists another breaker that can break two locks?
It's not completely analogous.
Ooh, I have an analogy for this.
The reason it's not completely analogous is say you're saying that I have an adversary that breaks this lock.
Yeah.
This has the same lock, but I can't break the other lock necessarily. So it's not perfectly analogous. What were you gonna say?
Okay, so say you have like a set of doors, like one behind another. The closest one in would be the least secure. So when the further out you are, the stronger notion of security you have.
Kind of.
Yeah. So like say for IND $ security, you're 4 doors away. For LR security, you'd already be one more door in. So you would already be past the IND $ door. So you wouldn't have to break that one.
I have no idea if that makes sense. What do you think, James?
It makes sense to me. I got it.
Seems like a philosophical question.
Does that make sense to you?
Of course, computer
Well,
scientists are also
think about it.
philosophers.
Let me
Don't
think about
let
it.
anybody think you're something different. Because you're all logicians, by the way, at least.
The most.
We're also scientists.
Let's not focus on metaphors. Let's focus on that which we know how to prove.
I'll write down my midterm.
So if we have a way to break, so the reason we need to prove the contrapositive is that in our reduction, so we have this, we're going to specify what A does in the reduction, right? A has an oracle. Let's call it F. She could ask single message of this, right? Because she's playing the indie $sign game. So she has this oracle, but then she also has she can also run the adversary. There exists this adversary B. We know what we suppose that it exists. So we can kind of use it as a black box. So in whatever her strategy is, she can play games with this B, with this thing that's given to us by assumption. Now, by assuming that there exists this probabilistic polynomial time adversary B, such that its advantage is non-negligible. If this we would then have to analyze what is A's advantage, and it's going to be derived from whatever B's advantage is. So her advantage is going to be a function of B's advantage. So this proof looks a lot like the one that James did last week in class. I would encourage you guys to do it on your own. You're going to end up with, so this is the asymptotic statement. This doesn't tell us a lot. And Professor Rogaway would get really mad if we found out that we were emphasizing it right now. A better way to express this kind of stuff. So sort of the same theorem, you would say concretely, there exists a reduction, which we denote with this funky symbol. This is going to specify what A does. It's going to use B as a black box, such that for every LR adversary B, the advantage in the indie $sign sense of A, which is specified by this reduction that uses B as a black box, is greater than or equal to 1/2 times the advantage in the LR sense of B in attacking the same scheme. You happy, James? This is the concrete statement of the same theorem. These statements are, in a sense, they intend the same thing, although they have a different form. This is more interesting because then we can talk about concrete things. This is saying, well, as long as K grows forever, if we have security in this sense, we have security in this sense. But in practice, K is a fixed number. Questions about that?
So comparing the difficulty of this reduction to the difficulty of IND $sign to IND1 or IND2, would this one be harder, or?
I think it's cleaner. This one, it looks a lot like when James did LR implies, no.
IND2 implies LR.
Yeah.
This one looks a lot like that?
Yeah.
Okay.
I'm happy to do it for you guys, but I'd like to ask more general things.
Fair enough.
What do you guys think? Questions about that?
I think other things would probably be better.
So this reduction specifies the adversary A. So when you're doing reductions, when you want to prove this notion implies this notion, you're going to be reducing an adversary who plays this game to an adversary that plays this game. And that adversary is going to use this adversary as a black box. In particular, this B expects to have a world where it's given an oracle, and it's trying to figure out which oracle it has. However, we have to simulate that oracle. So how do you do that? That's the tricky part of the reduction. Again, for the purposes of this midterm, I think the main thing you should focus on is notions of security. But you want to have this reduction stuff in the back of your head because it's part of all of it. knowing how, you should be able to in particular say, are these two notions equivalent? Why are they not? Why or why not? Things like that.
We need to know modes of operation stuff.
Yeah. Yeah.
I have a general question about these notions of security.
Excuse me.
So these
It's
are
really-
like general notions of security, right?
Yeah, I can
$I
answer this
$,
question.
LR,
Is there a
sort of like the
question?
perfect privacy and the Shannon notions that we were learning earlier. Because I know some of them were specific
Maybe
to
after
block
this
ciphers, but
answers.
these are just like general for any kind of encryption algorithm.
These are for, the goal of an encryption scheme is very different from the goal of a block cipher.
Right.
So that's why we define them differently. They're not equivalent objects at all. Our goal with an encryption scheme is
Oh,
that.
okay, so these are encryption schemes. Okay.
And a block cipher is a block cipher.
Right. So that's why you're comparing it specifically to a permutation.
Yeah.
Permutation. Okay.
Right, because the goal, the intention of a block cipher is that it's indistinguishable from a random one.
So, Vickers, just spare me some time to answer Kevin's question.
Yeah, sorry.
About that lock things. In fact,
Yeah,
you're
James, you
trying-
should just talk for a while.
I think you're trying to think of encryption schemes as locks, right? When we say a lock is secure, let's say we have different security notions in our class. You can think about those as the attacking power of me who wants to break this lock. For example, in IND dollar, I am allowed to use screwdriver or knife to break this lock. But maybe in the other weaker definition, I am only allowed to use my hand. So I agree that if I am only allowed to use the hand, that will be a weaker security notion, because that lock is only supposed to be against a weaker type of attacker.
It's a good metaphor.
I like it.
So if I can use my hand to break a lock,
That
Which
doesn't
is a weaker?
necessarily mean that, well, I definitely can use a
so
screwdriver.
remember
for
that
the
in
same
our
purpose.
when we say strong implies weaker, we are talking about same kind of lock, same kind of encryption scheme. If this thing implies a weak, if I can use my hand, then of course I can attack it. In the strong sense, I don't even need to use the knife or the screwdriver. I can still break it.
With just your hands. Yeah.
Right. That's some sort of if I break the weaker notion, I also break the strong notion. Does that somehow answer your question a little bit? Maybe making you more confused. I'm not sure.
I'll think about it.
It's a good metaphor.
I have a,
That's confidence worthy.
can we go over the notions of security that we've like gone through in the class, just as like a brief overview in order?
PRG.
Yep.
PRP.
Can you write out KR?
Yeah, I can write out KR. KR is really easy. So, what kind of object is it related to? Is it useful for it? Block cipher.
Yeah.
We have the block cipher E. And what is A doing in this experiment? She is, well, we choose a random key, and we give A Oracle access to that thing. So she is basically asking queries of this, and then she tries to output, this should be a semicolon for those following along, then she outputs a string K prime, which is her guess of what the key is. And what we're interested in is the probability that K prime, her guess, is equal to the key we generated in the experiment. So does this imply PRP security?
No.
No way. What about the other way? What about the converse?
Yes.
All right. So,
And then I guess unforgeability would be next.
unforgeability is a very similar thing.
Yeah.
It's called
Unpredictability?
Unpredictability, yeah, let's.
Oh.
Professor Rogway keeps calling it unforgeability.
He like went back and forth on it.
Yeah.
Yeah, nice.
It's like forging, but. Okay, so we do the same thing. We generate a random key, but this time A is going to output a pair of strings. And which these have to be n-bit blocks. and she wins, we're interested in this time in the probability that E sub k of x is equal to y. So here's something that a lot of people didn't understand on the homework. The goal of the homework was to show that PRP security implied unpredictability, right? So in class we proved that PRP security implies KR security. And the homework, the goal was show PRP implies unpredictability. So if you're given this, do you know anything about this, whether this is true? So a lot of people said, if I prove, what do people do? So some people thought, well, I'll prove that unpredictability implies KR security. Does these two things imply that? No. You would have to prove that if you can prove that KR security implies unpredictability, then you're golden. That does in fact imply that. But I don't know if you can do this.
This is false.
I think that's false, right?
Which is false.
Yeah, I don't think it's possible.
Well, yeah,
So, you could probably separate that. So how would you show something does not imply security in another sense? So you'd say, suppose there exists a, oh well, never
You are
mind.
separating. In
Yeah.
fact, think about identity permutation.
Exactly, yeah.
In that case, it's KR secure because you can only guess the key.
Right.
And you have a very low probability of guessing correct.
But what about
it's
it?
UNP because you can always predict when type of cycle.
Yeah.
So that means not true.
Yep. Okay. So I wanted to quickly run through non-space encryption and then authenticated encryption so that you all are thinking about those things. So non-space encryption is when we write out the advantage, it's going to look nearly identical, so I'm not going to write it out again. But what is A given access to? Anybody? What is A's universe?
What?
So we're talking about the security of non-space encryption schemes.
that's two oracles.
It's two oracles. What are the two? I think you're thinking of authenticated encryption.
Oh.
Fact track a little bit. Non-space encryption. No authenticity
Okay.
expectations. So E is given an oracle that has two inputs. The first input is the nonce. The second is the message we want to encrypt. So she queries these pairs NM, and then she's given ciphertext back in response. What is she given in the fake world? What do we do in the fake world?
It's same thing, two pairs.
Two pairs. And what does the fake oracle do?
Random.
This generates a random string of the appropriate length. Of the appropriate length. And what does that really mean? That means you should be able to compute the length of the ciphertext from the length of the message. That's a sort of small, sufficient condition for this security thing being well defined, for this experiment being well defined. So the restriction on A is that she's never allowed to repeat a query with the same nonce. Okay, now we're going to talk about authenticated encryption. What is the goal of an authenticated encryption scheme? It's to encrypt and then and not be able to forge ciphertexts, right? So I receive this message and I know that you must have the key that was used to encrypt that thing. So in this game, we're given a pair of oracles. And so the syntax remains, has a nonce, right? So we're sticking with that syntax. We give, the first oracle we give her has this syntax, this signature. She gives it pairs N, M, where N is a nonce and M is a message. The other query is a decryption oracle, which has this a similar signature. This is pairs of nonces and ciphertext. In the fake world, we give her this random oracle as the first oracle, and then a bottom oracle. What does the bottom oracle do?
It outputs bottom.
Whenever you ask it something, it's just going to output bottom.
Shows you it's bottom.
But why do you think that is? Why would you make such a stupid condition?
Because hypothetically speaking, most things should decrypt at bottom if they're not valid.
Good answer. All right. Now, there are a couple restrictions on what sort of queries A is allowed to make. Who can tell me?
You can't like encrypt something and then try and decrypt that to what you get back.
Right. So what is in particular the restriction?
You can't like if you pass M and you get a C, you can't pass that C again.
To D.
Actually, it's a little weaker than that. If you ask an encryption scheme with an encryption query with a particular nonce N, you can't decrypt with that same nonce.
You can.
You can't.
You can decrypt with the same nonce as long
As long as you have the same different message, yeah.
Oh, you're allowed to. Okay.
You're allowed to ask encryption oracles to repeat it.
Never mind.
So wait, what was it?
That's why we did this together.
You can't have the same nonce and M.
You can have the same pair.
They hear it.
So I can have
Big nonsense, E and D, right?
Right?
Yeah.
Why don't you write it big on the
so
other
you,
board?
you could ask E and M and then ask E and prime and prime is
The first condition is that it's a little bit hard to write them in terms of mathematical encryption. But so for all decryption queries, you just write it in. For all decryption queries and C, there should be no previous encryption queries. And M such that encryption oracle returns C. Is that clear? For all decryption queries and C, there should be no previous encryption queries. N with the same nonce here. And any message such that it is encrypted with C. Basically, it's just a condition, the least condition that prevents triple bits. Since if you can decrypt this thing, you know that it will always get back to the plain text message in the real world, but in the fake world, you will always see bottom.
So what's the second condition?
Second condition is that nonces should not be repeated for encryption queries. So,
Maybe you can ask decryption with the same nonce. Yeah.
distinct nonces. For encryption oracles.
But you can repeat for decryption?
You can repeat for decryption, but you can't repeat for encryption.
I messed that up.
It happens.
Any questions?
Yes.
Yeah, we gotta talk about that homework real fast.
For all of this for the midterm too? Everything up to today's
Like 6:15.
Of course, there will be, like you said, less emphasis on the
I told
newest
him we
material,
probably won't be done till around
but you
6:30.
should know what a Mac is.
It's the newest meeting.
This week, yeah,
hate
including,
Macs.
including today.
That guy's awful.
Yeah.
So I have a question about the encryption scheme, for like the authentication one. So we know what kind of messages they take, right? And what kind of nonsense they take. So is there ever a case where you know that it takes this kind of message, but is there ever a case where it doesn't take a similar message of the same length?
So remember when back in the day when we were talking about perfect privacy, Professor Rogaway gave two conditions that allowed us to talk about the three different notions being equivalent. One of those was reasonableness. That basically means if for some key and some message, if you can encrypt that message under that key, that means the encryption algorithm doesn't output bottom. That implies that for all keys and messages of the same length, you should be able to decrypt. Oh no, sorry, excuse me. You should be able to encrypt. So that just makes encryption schemes easier to work with. When we know they have these properties, it's easier to analyze them and things like that. So that's the purpose of that.
So does that also apply to like ciphertext? So you go like this is the form of a ciphertext, so everything of that same form or length also gets decrypted, or is it only the other way around?
What do you mean by the other way
Like,
around?
I said like two messages of the same length, if one can get encrypted, the other one can as well.
Oh.
Okay, does that apply to ciphertext and decryption?
What do you think? What do you think about in the context of authenticated encryption? Do you think that's reasonable? Let's say I view a ciphertext. I change one bit in the ciphertext. Should we be able to decrypt that thing?
Maybe.
No.
It's certainly a possibility, but we hope that it's not very likely that decryption algorithm will not output bottom. Because we're basically doing a forgery by changing the ciphertext. So even just changing a bit, it should make it so it can't be decrypted. That's at least the intention of an authenticated encryption scheme.
Wait, but it can still be encrypted though, right?
Sure. Yeah, if it's definitely useful if you know that if you can encrypt a message of this length, you can encrypt all messages of the same length.
Okay.
And to be more concrete, usually the ciphertext is going to be longer than the message for AE schemes. And if you think about the map from message to ciphertext space, this function is in general going to be injective, but it only injects to a subset of the ciphertext space, and that subset is going to be small. So there should be, and you should be unable to guess which point those things are, except random guessing.
So we have a half hour left, or a little less. Now it's time for any questions about anything.
Are we going to need to know how to break certain operation?
Ooh.
In what sense?
Like, you know, given a CVC chain or zero, maybe, I don't know, like, you know, put just in English, say how you would go about breaking it.
Yeah.
Yeah, I think so.
That's definitely.
You are supposed to be able to answer some simple attack.
Yeah. So for example, like how do you? Let's actually draw out CVC mode.
Say forge the CVC map when the CVC accepts variable length of input. The attack will describe that class. If you ask you that question, please describe me a way such that you ask two queries and you only ask one query and then you can directly forge. You should be able to answer that.
So message 1, message 2, message 3, and then here's the IV. So this is what the output ciphertext looks like for CVC mode. Here's your IV, which is, let's say the block cipher is a permutation on n-bit strings. So the IV is going to be n bits long. What are the different ways you can choose the IV?
Randomly?
So randomly, so that works, right? What if you have a counter? So the first IV is 0, the second IV is 1, etc. So who can tell me why that's not a good thing to do?
Just
Ignore cover stuff.
yeah. Just repeats.
It doesn't answer all the questions.
It's like the determinism in it. Like if you know for a specific number that M1 encrypts to a specific C1, then you can choose an M1 such that you'll get the same input into the EK, and then if it's the same.
Yeah. So you just change your message so that it incorporates that new ID. That's just incrementing.
Remember, for answering that question, it's better to give concrete things. For example, first ask all 0 message, and you know the IV would be 0, and you know that C1 would be encryption of all 0 messages. Next time IV would be 1, right? So how do you choose M1? You choose M1 to be what?
Well, M1 and then M1 XOR 1 has to be 0, so
M1 is what?
1.
Yes. Yeah. Try to answer your question in this fashion.
Okay.
It's always better than just giving some general sentences.
Yeah, it's also easier to grade. Give you more points.
Yeah, it's just,
So,
Man, I feel bad. You guys have to grade
So
my
you
handwriting.
just have the
I
message
feel bad. You guys have to grade my
equal
handwriting.
the IV every
I
time.
try really hard, but it's
in
not
fact,
good.
Wait, if the IV is like 1, you have the messages.
Oh,
1.
I'm talking about first.
Or what do you
Midterm.
do?
oh,
the IV is 1, what?
But what
Not
do
much
how
you
do
can
you
do
pick
about
the message you're gonna feed into this?
I wish I could make a typeset.
You just choose these blocks M1, M2, and
Just have a bunch of
M3
stamps.
all the way for any arbitrary number of blocks.
That'd be so dope.
Yeah.
Dude, you think about it. If you had like an app that like created a signature
Yeah. So for
based
for
on text
for
stuff,
CVC mode,
wouldn't that be dope?
at least if you're
Be so cool.
generating a random IV, you must transmit that random IV. If you're doing a counter thing, and so both the receiver, both the encryptor and decryptor are maintaining state, then you don't need to transmit the IV.
So then an adversary would know that like this first part is the IV.
Yeah.
Kirchhoff.
But then
Kirchhoff.
that wouldn't be enough.
Huh?
That wouldn't like help them at all.
Well, what do you know? What do you know if you know the IV? You also know the message. Remember, it's a chosen plaintext attack. So you know this and you know this. So you know the inputs of the first block cipher call. But you don't know, well, yeah. Yeah.
So wait, I don't
Just
get
try
it.
to repeat.
What do you mean?
Oh, like how do you know from changing M, you know what you
Okay, it's not, yeah, I didn't finish describing that attack.
okay.
So change M1 to 1, then you get another output. You see if these two outputs are the same. If they are the same, you say you are in the real world. If they are not, you say you are in the random world.
Okay.
Because in the, remember for IND dollar, that dollar oracle always tells you independent random strings, right? So it's really likely that they are different. But in the real world, it's always going to be the same string. Same input always map to same outputs for block package.
So let's name our oracle for the purpose of describing the attack. So this is the adversary's strategy. She first asks for encryption of the n zeros. Let's call the oracle F. I like that. And we get back this C naught, this C, right? Let's suppose, so for this thing, we're not transmitting the IV because it doesn't really give us any information. Although it doesn't really matter. But, so what do we do next?
Since it counts up by 1, ask a message of 0 and minus 1 concatenated with 1.
0 to the n minus 1 concatenated with 1. Because, why?
The XOR of the next IV and that should result in the same ciphertext after going through the block cipher.
Right. So, in particular, you have these two strings, C and C naught. C and C prime. What do we do? What do we output if they're equal?
You got the real oracle.
Exactly.
Very high chance of it.
Yes. If C is equal to C prime, then output 1. We believe we're in the real world. If we're in the random world, so we're thinking about ND dollar sign. If these are different, then, well, we must just be getting random outputs.
You just output and return two different things.
Yeah, that's fine. Questions about that? Yeah, why don't you?
I just have a question. After this, could you go over the different kinds of attacks? Like chosen plain text attack, chosen ciphertext attack, and like when you would use which to determine security?
The question should be clear about what notion you are attacking. So by attacking, we really just mean following that game, design an adversary.
So in particular, we can't do a chosen ciphertext attack if we don't have a decryption oracle.
Yeah. Okay, so it's your types of attack are based on what you have for the problem.
Yeah.
Which makes sense.
Shouldn't why the one? No, that's M1. M1 is the last. If it's 1, then the last bit will be 1.
It's a crappy encryption scheme.
Wait a minute. The IB is 1. The IB is 00001.
Sorry.
No, it
We're
works.
binary.
It's
We're
just
not writing
slow. So you have to change the block cycle.
Oh, we're not normal people. We're binary.
So AES, when implemented in hardware, it's just an instruction that takes like 7 cycles, and you can do instruction level parallelism with it. So you can execute, you can send an AES call at every clock cycle and just blast it through. You can get full, you have full parallelism. For example, with counter mode. So counter mode's cooler.
Shouldn't it be if C does not equal C prime, then output 1?
That's value.
Because if you're XORing 0 and 0, you would get
so for the
0.
first query,
0 and 1, you would get 1. So then you should output 0 if they're equal, right?
So for the first query, what we input to the first block cipher call is 0 XOR with 0, right?
Yeah. Because the counter is 0 initially. Yeah.
Okay, and so for the second call, the IV is 1. And if we want it, what we're trying to figure out is if we get the same thing.
Oh, right, the counter increments. Okay.
Yeah, the counter,
All
exactly.
Right. Never mind.
Yeah.
Okay.
So it counts.
Yeah, that's going to be the most, but it's basically the format of the quiz, just longer.
So wait, the homework says to like construct a block cipher from another block cipher. So you couldn't do something similar to this for that, like
we don't have an IV.
They say make one twice the length. You couldn't do that with like 2 boxes for that. Would that work?
So this question has come up so many times in office hours. It's probably a good time to talk about it. So the question is, So you have 2 block cipher calls, right? So what do? You split the message in half, and is this your proposal? Just I'm asking because.
Well, no, it does the thing where it goes.
Oh, you do like XORing things?
Yeah.
Okay, and these are the same key?
Yeah.
Alright, well, so let's attack this thing. Or try to attack this thing.
But with randomized.
Remember, we're trying to...
Well, you don't have an IV.
Well, you don't have an IV because it's a block cipher.
Oh, okay, got it.
Yeah, so we're trying to distinguish this thing from a random permutation. How would we do that?
Let's say M1 is all zeros in the first attack and M2 is all zeros in the first attack as well. And then the next question I ask is M1 all zeros, and then M2 is 0 minus 1 concatenate 1. So the first half, if you're real, you'll get the same C1. If not, I'll get a random jumble. And I'll know with a very high probability that it's fake.
Right. Yep.
Okay.
That's it.
Fix this by setting up a spliceful network right here and jumbling up the messages and then feeding that.
I think that's a swell idea.
How many rounds do I have to do?
That's a good question.
How do I generate my pseudo-random function? My F.
Use a block cipher.
He didn't say that. If you wanted to look it up on the internet, I would totally encourage you to do that. There's a great paper that one
He already knew the answer.
found. I don't know if she's here, but
Rylan found that, right?
Rylan found it, yeah.
so did
Yeah, she's
Erin.
not here.
So did Erin. I don't know if she's here though. Okay, anyway.
What's the paper called?
It's a result from Luby and Rakoff.
Yeah.
It's
Wait,
posted
wait,
on Piazza.
Which paper?
I don't remember what it's called, but it's
About what?
Fucking nerd.
yeah, it's basically about like how many how many rounds of Feistel do you need to do
The paper
with the
by
PRF
hole.
to have it to result in a secure PRP.
Oh, that's no one.
Yeah, that paper.
Yeah.
Cool.
So if you're gonna use that construction, you better reference it.
By whom?
FYI.
I'm not
Referencing
sure.
is important.
I was talking about
Okay.
a different paper that he used that was for number 14. not
So that
for
sucks, right?
number 13.
Yeah, we did our own 13.
Yeah.
With Ronnie. So.
I mean, to be fair.
I mean, it's like that's what a lot of
basically.
people.
Yeah.
That's what I
But it
started
was sort of
with,
like,
and I started
I just needed to
attacking
see
that.
it written out. And got
Yeah.
it.
So what
I
if you
don't know.
already
I don't
have
like the whole
PRF
Feistel network.
instead of a PRF?
Uh-huh.
Then how would you wouldn't need, or would that same concept apply that you need a certain number of rounds?
Well, a PRP is just a PRF with but it's because a permutation is a function, right? So
Okay,
one
so-
subsumes the other.
Okay. So
Assumes.
they're like
That's
switchable.
a good word.
It's like not having.
Not in all contexts, because a PRF you don't necessarily have invertibility. If you need invertibility, you gotta have a PRP. Other questions? 10 more minutes.
What are the answers to the midterm?
Just put a happy face for all the questions.
I'll make sure to do that.
Is there gonna be another extra credit question?
I plead the fifth. I don't believe so though. No, there's not another hokey extra credit.
Ah, so you have seen it.
Yeah.
He admits it.
How well do we need to know finite fields for this one?
Review it.
Review it?
Yeah. Review it. Yeah. Because we still need finite fields. We just talked about it today.
Yeah, finite
It's
fields
part
are
of
good.
cryptography.
Oh yeah, so today in lecture I walked in 10 minutes late, and he was just saying about how the normal CB, not the CMAC, not the Weigman Mac either, but the one before it, I think you continue from lecture 17.
CBC Mac.
CBC Mac,
A simple thing why that doesn't work.
He said something about the finite length of a string, and then that was like when I kind of lost that one.
So what he was trying to say is that for fixed length, so if you imagine an experiment where the adversary is only allowed to ask a message of some fixed length,
Mhm.
then it's a secure construction. But if you allow it to be an arbitrary length, it's no longer a secure construction.
Okay, and then we move to the Carter-Weigman Mac because that one takes multiples of n.
In fact, there is a construction called CMAC, which he described, which is based on CBC Mac, but it's more refined, and that works on arbitrary length strings.
Okay, so the I was just trying to understand why he moved from one to the next one to another one. It was because it couldn't take in arbitrary length messages.
No,
So let's write out the results. CBC Mac. Works. What does it mean for this thing to work? What is the security notion we're talking about for Macs? Sorry?
Authenticity?
Yeah, but what does authenticity mean? What is the experiment that we give the adversary?
That two messages won't match to the same thing, right?
It's called unforgeability.
Unforgeability.
So the property of a Mac scheme of Mac is supposed to be the advantage of A, adversary A, in attacking a Mac, which we call F. Oh wait, let me back up. What is the signature of this thing? A Mac F is a map from what to what? Anybody?
Whole process of trying to do different constructions. You
Yeah.
first talk about something like
So then it's trying to
you first talk about something like this.
a smaller length
This is called Carter
or a
Weigman.
different length string.
In fact, we take in a key, so that's necessary. And then we should be able to do it with arbitrary length strings. So any finite string. And it maps
Why we go
to
from here to here?
some fixed length.
CBC Mac only works for fixed length.
So now what is the
And
security
for fixed
property?
are multiple of them. It would work for
We
very
generate a
different
key,
processes.
we choose a random key,
Weigman Mac.
and we give a access
no, this
to
already works for
this F or
all,
F sub k oracle.
for all limbs that are multiple of the blocks.
Yeah.
For CMAC already works for all.
So she gets that I have a
messages,
string
even though
and I
not
get
each
its
one.
tag back.
Yeah.
What is her goal? Anyone? So what is a forgery? She's going to output something. So she's going to output a message tag pair. Sorry, this is really ugly. Let me write this a little more clearly. So the advantage.
I just like to say the future on the Facebook session since
Okay.
I believe it will bring the third.
What do you call this, Mac?
And that will be very much.
Is that what you called it?
I forgot.
Okay.
No, I'm fine with it. It existed. But I'm already in 5 minutes organization. So, might as
So
well.
she's going to output a message tag pair after playing around with her oracle. And what we want to know is, what is the probability that f sub k of m is equal to t? However, we have to make a restriction on this. What is the restriction? She never asked m. A
This looks so much like that thing.
Okay, so CVC Mac, does it work? Is it secure with respect to this experiment?
No. You also have to specify that you have a fixed length m
Right.
of m blocks.
So
Or
if we
smaller.
were gonna talk about the security of Mac, we would also have to restrict the length of our queries, right? CMAC,
What does the C stand for?
chain cipher block chaining.
No. In CMAC.
It's the first letter of CBC.
Yeah.
Okay. So it's like CBC Mac except for.
Yeah. So the reason
That's-
for this
that's
is
ugly.
that there's
I
a
don't like
bunch
that.
of Macs that start with some letter and end with Mac. There's CMac, there's PMac, there's HMac, there's UMac. There is, well, I think that's it.
T-Mac and O-Mac. T stands
T-Mac
for 2 and O stands for 1.
I
Which was just a, yeah, I'm telling the truth.
Cryptographers are horrible at naming things.
We
can
noticed.
tell. There's CVC Mac and CMac, where C stands for CVC Mac, but it's not CVC Mac.
Right.
You got it.
You got it?
You're learning in this class. That's cool. Okay, and then
No need to hate.
so what Professor Rogaway was talking about today is that this is a special case of a more general construction, which he called the Carter-Wigman construction. So what is that? So first of all, you're composing an epsilon almost universal hash function with a pseudo-random function, or like a PRT or something.
So I don't mean to interrupt, but I just want to clarify like what I'm understanding. So when he moved through the different types of Macs, they all satisfy the Mac property, as in they're equally secure. However, they work for the length of the message becomes more flexible.
Right.
Yeah.
You can
Yeah?
understand in terms of
Okay.
So for the exception is CBC Mac. For CBC Mac, we have to restrict the length of the messages. For CMac and the polynomial evaluating thing he was talking about today, the length of the message doesn't matter. It's the same. It's the same
The
construction.
polynomial evaluating thingy.
Yeah.
Polynomial only works for integer multiples.
Yeah.
Well, but you can pad it.
Why do you pad it with ones and zeros?
Okay.
Why do you pad it with ones and zeros?
Or one followed by zeros?
Well, why do you need to pad it? That's the first question. So looking at the because you need to have an input that is n bits long.
No, he's asking why you need to pad it in that way.
You know,
Because,
I don't know why you need to do that for Macs. I know why you need to do that for encryption.
You need to do that, of course, because you need to make sure different messages gonna pad to different gonna need to pad to different things. If they pad to the same thing, it's easy to forge, right? If it's all zeros, say,
Yeah.
then
Yeah.
let's say you decide
Yo, it's Nick.
your first query asks just a 1-bit message. It's padded with n-1 zeros.
It's
You
like an hour and a
next
half.
ask a second query that follows the first bit and then a 0. It's still gonna pad to the same thing, right?
Right? Getting what I'm saying? Yeah.
Yes.
And you can easily forward that, right?
Boom.
Any other questions? We have time for a couple more. You haven't said anything.
Diagrams are we expected to draw?
All.
All.
All the time.
Modes of operation for encryption. Modes of operation. So you should know about the CBC MAC construction. Yeah, you should also know the CMAC construction. It's just it's a simplification of the CBC MAC construction. It's just a little simpler, right? So yeah. So you should know the MACs that we've learned about and the encryption schemes we've learned about.
So a couple, 3 pictures or something maybe.
Yeah, and then Feistel networks. You should also know about Feistel networks. Yeah.
The polynomial hash function that he had us do, is that fair game? That he talked about today?
It's so fresh that you're not going to need to know a lot about it. I wouldn't emphasize it when you're studying.
Fair enough. Gucci then.
Just going off the same question, do we have to know how to construct a polynomial? Because that kind of lost me at that.
Yeah, don't worry about it. It's that's pretty fresh. Like that was like the last 5 minutes. So.
Super.
All right, folks. I guess we're out of time.
It's a pleasure.
Thanks for coming. Nice and big. I thought like 4 people were gonna come.
So many people are lost in this class.
It's a hard class.
Yeah. Shoot. I would think of a medical.